Can I ask a question before we start?
Yes, sure.
Doctor, could you please consider removing the shear and bending moment from the final?
Look, it's an important part. We cannot remove it.
But we will have to go back to the statics, and there really is no time. Today we finish this chapter, and the final is next week. So could you please just think about it؟ لأنه عن جد صاروا كتير كتار، صاروا 4 chapters. وقبل كنا عم نعمل 2 chapters per exam.
It would help.
Okay, I will see what to do. Okay, thanks. Okay, so now last time we have introduced the principle of work and energy, and we have done some problems. So we will continue with problems today. First, blocks A and B have a mass of 10 kilogram and 100 kilogram respectively. Determine the distance B travels from the point where it is released from rest to the point where its speed becomes equal to 2 meters per second. So in this problem, we have two moving blocks A and B attached to a system of pulleys, and we need to find what will be the distance traveled by B when its speed becomes 2 meters per second. So here we have solved a similar problem, if you remember, in the previous chapter, okay? And we used chapters 12 and 13 to solve it. We have considered the free body diagram of A and B separately, and we have considered all forces acting on them. And then by writing a system of equations, we solve for the acceleration. Here, using the work and energy will simplify a lot the approach, okay? So instead of writing several equations, finding acceleration, then using relation between acceleration and velocity, we can obtain velocity by just writing the principle of work and energy. But also we should pay attention that we still need to use the pulley, the formulas for pulleys. So we should write the total length of the cord and to relate the motion of A to motion of B. Okay, so here let us start by relating motion of A to B. We will follow the cord. So we have, when going from A to B, we have first SA. Here we choose two coordinates, SA and SB, because A and B are the moving objects, okay? And these pulleys here are attached to B, so we can take SB just to the center of these two pulleys, while the other two pulleys are fixed. So we will take the reference passing by the center of the two fixed pulleys, and we have coordinate SA downward for A, coordinate SB downward for B, and now we will calculate the total length of the cord. So if we write the total length of the cord, we have SA plus we have 1, 2, 3, 4 SB, and of course plus a constant, but as I told you before, the constant will be, when we derive, the constant will be eliminated, okay? So we can write that just 1 second. We can write that here SA plus 4SB is equal to a constant, okay, is equal to a constant. So if you derive, you have that VA plus 4VB equals to 0, okay? And also if I need a relation, here no need for a relation between acceleration, but if I need it, I can find it. I should also tell you that SA plus 4SB equals to constant. You can use it also for displacement. And you can say that delta SA plus 4 delta SB is equal to 0. Why? Because you have VA plus VB equal to 0 at any instant. Okay, so if the relation is valid between the instantaneous velocities, then it will be valid also for the average velocities. And by definition, what is the average? It's delta SA over delta T. So here, if you put delta SA over delta T plus 4 delta SB over delta T equals 0, since it's the same delta T, you can simplify delta T from both, and you get that delta SA plus 4 delta SB equal to 0. This means that the displacement of A can be related to the displacement of B. Okay, so now I will remove delta T because it's the same. So I get the relation between the displacement delta SA plus 4 delta SB equals to 0. Okay, now as a next step, now I found a relation between velocities and acceleration. Now, if I want to apply the principle of work and energy, I will choose a system that will simplify my calculation. And if I just take A alone, it's not good because I will introduce a new variable which is the tension in the core. And if I take B alone, I will introduce the tension here. Okay, and of course the tension is the same everywhere here, but I will add an unknown which is T. In order to avoid adding an unknown, the system I will take will be the whole system, the whole one. Why? Because if I take the whole system, the internal force of the cords, the forces in the cord will become internal to the system. And only I have external forces, the reaction at the support here, here and here and here. But who will tell me why I don't need to find these reactions at the support? If you are doing work and energy, what will be work of these forces at the support?
Zero.
Zero, because for work we should have displacement. Okay, these forces are acting on a fixed point, on fixed points, so they will not produce any work. So the only two forces producing work are the weight of B and the weight of A. Okay, so these two will produce a work on. Okay, now what we will do, we will write the principle of work and energy. Okay, so the principle of work and energy is T1 plus, here if you want, T1 is the initial kinetic energy of the system, so we should put sum of initial kinetic energies, okay, plus sum of work of forces. Here we have two forces doing work, so we have the work of weight of A plus the work of the weight of B, okay, equals to summation of kinetic energy T at state 2. Okay, so now initially my system starts from rest. As I said, it's released from rest. Because it is released from rest, then summation of T1 is 0 because initial kinetic energies are 0. So here this term is 0 since starting from rest. Starting from rest. Okay. We still have the other terms, work of A, weight of A, work of weight of B. So first, look, here we have considered coordinates downward as B down and as A down. Okay, for downward coordinate, what is the expression of the work? If you remember, when we derived together the expression of work, we said it is minus W delta Y if Y is up, and plus W delta Y is down. So here, since S is down, we can say that the work of weight for any of the two is equal to plus W times delta S. Okay, so I will apply this relation for A and I will apply it for B. So I get that W of A times delta SA plus W of B times delta SB equals to, at the final state, we have the sum of kinetic energies. So we have half times mass of A times velocity of A at state 2. So if you want V2A squared plus half mb times velocity at state 2 of B squared. Okay, so in this equation, what are the unknowns? First, here they said we want to calculate the distance B travels when its speed becomes to 2 meters per second. So what is V2B? V2B is 2. So we know the value of V2B. V2B can be replaced by 2 meters per second. Okay. Now, don't forget that we have related velocity of A to velocity of B. Okay. We said that VB, we have that, if you remember, we have VA plus 4VB equal to 0. Okay, plus 4VB equals to 0. This means that velocity of A is equal to minus 4 velocity of B. And since here B is moving downward with a velocity of 2 meters per second, okay, then we will have that VA is equal to minus 8. Okay, it's minus 8. So A will go upward, okay, and B will go downward. So here we can replace VA in this relation here. We can replace it by its value, which is 8. Now, we still have two unknowns, which are delta SA and delta SB. Our final purpose is to find the distance traveled by B. So what we need to find is delta SB, okay? And to remove delta SA, we can express it function of delta SB, because also we have demonstrated from relation between motion of A and B that as we wrote VA equals minus 4VB, we can also write delta SA equals to minus 4 delta SB. Okay, so now all we have to do is to replace delta SA by minus 4 delta SB. Okay, and then the only unknown will be delta SB. We can calculate it. So as you can see here in work and energy, you just need one equation. Okay, of course, in addition to the relation between VA and VB and delta SA and delta SB to solve your system. If you use the previous chapters, it will be a little bit longer because you should write the equation of Newton law for A, the equation of Newton law for B to find your acceleration, and then from acceleration you should use kinematic relation to get the distance. Okay, which as we did in the previous chapter. Any question on this problem?
Doctor, I have a question.
Yeah.
In the equation of the work and energy, why SA is not in the opposite direction of SB?
In the equation of work and energy, because SA, look, it's an algebraic value, delta SA. Okay, it can be positive, it can be negative, but the coordinate is directed in which downward for both. For both, S is downward. Okay, so for both, the expression of the work is W delta S, but since delta SB is positive, then the work for weight of B is positive. And since delta SA is negative, then the work for on block A will be negative. Okay?
Okay, okay. Thank you, doctor.
What's your name?
Naim.
Naim. Okay. Okay. Now, power and efficiency. Power is defined as the derivative of work with respect to time. Okay, so it's du by dt, and as we know, the elementary work is F scalar displacement, scalar dr. This is why we can say that if we divide by dt this term, we will get F dot dr over dt, and dr over dt is the velocity. So the power is F scalar product V, and the unit for power is watt or joule per second. Now, what about efficiency? Efficiency is the power output that is useful over the power input. So you know that in any process we might have losses. Okay, so the efficiency will give us the ratio of power output over power input, and will tell us the percentage of energy that is used. Okay. Now, of course, if we have the power output and input taking place during the same time, then you know that power is energy over delta T. So delta T will be simplified, and you get that the efficiency is energy output over energy input. Okay. So now let us do a small problem on this. We have the motor operates with an efficiency of 85%. Determine the power that must be supplied to the motor to lift this 375 Newton crate at the instant point P on the cable has an acceleration of 1.2 meter per second square and a velocity of 0.6 meters per second. So here in this problem, we have a pulley system that is operating, okay, and it's trying to lift this box upward. So we want to lift it upward, okay, and we have the motor M is driving the cable inward in it, okay, in order to lift the crate. Now they gave us the efficiency of the motor, and we want to determine what is the power supplied, and what is the input, if you want, in order to accomplish this objective. Okay, so first, what is given? We know that for P, the point P at the motor level has an acceleration of 1.2 meter per second square and a velocity of 0.6. So these are the properties at point P, AP and VP. Okay, so we have acceleration of P and velocity of P. Okay, so now let us try to relate the motion of C. Whenever you have a pulley system, directly try to relate the motion of points P and C together. Okay, so what we have here, first you have, since you have a motor, okay, for the motor, since it's pulling the cable inward, then you will take a coordinate for the motor, okay, and this coordinate will not just consider this distance, because you know this distance here is constant to the motor, but what is changing when the motor is pulling the cable is going here, and it's turning about the motor, okay, it's entering inside. So the coordinate for the motor will take into consideration the total length that will enter inside the motor, and we will call it S of P. On the other hand, we have the block C that is moving, so we need a coordinate for it, and since it's moving in the vertical direction, so we need a coordinate for it, which is S of C. Okay, so you have S of C. Now, as a final step, what we will do, we will try to correlate motion of points C and P. Okay, to do this, we will write the total length of the chord. So if we write the total length of the chord, what do we have? We have here SC plus SC 2 times, and SC plus SC. Of course, we have constant, the constant around the pulley, and here you have a constant, but you can lump all constant in one part. And 2SC plus what? Plus the length that is going inside the motor, which is SP. So you can write that for the cord you have that 2SC plus 2SC plus SP equals to constant. So now if you derive, you get that 2VC plus VP, 2VC plus VP equals to 0. And if you derive again, 2AC plus AP equals to 0. Okay? So now, from here, you related velocity of C to velocity of P and acceleration of C to acceleration of P. And since they gave you AP, then you can deduce AC from this, okay? So you can say here you can say, so VC is equal to minus VP over 2, which is equal to minus 0.3. And why it's negative? Because C will go up, okay? C will go upward. And you have that acceleration of C is equal to minus acceleration of P equals to minus acceleration of P over 2 equals to minus 0.6, minus 0.6. So it's accelerating but upward, okay? This is why it's negative. You have VC negative and AC negative, so their product is positive. This means that you have acceleration, okay, but upward acceleration. So now we know the information about acceleration of C. What they want us to find is the useful power, okay, and the at this instant, okay. To get the useful power, by definition, what is first P useful, okay? What is the power useful here? What is my purpose in this problem? My purpose is to lift my crate, okay? So to do this, I should develop a certain tension in my cable, okay? And we know that, as we said, the definition of power is T scalar T dot V as vectors, okay? T dot V. And since here they are collinear, okay? So you can say that here I will put that they are vectors. So it's the scalar product velocity, okay? And so these are vectors, okay? And once you do the scalar product, the angle between, you will apply this formula for useful power or at point P or at point C, you will get the same result, okay? Because here, what you are doing is you are putting a tension in the cord in order to move C or in order to move P. And it's if you do the power for C or the power at P, it will give you the same result. So here I will choose P since it might be easier. So you have one tension here, okay? You have T, and you have the velocity of P given, okay? So you can say that it's equal to the magnitude of T times the velocity of point P times cosine 0, because they are along same direction and they have same sense, okay? So it's equal to magnitude of T times velocity of point P. Now, concerning T, we don't know it yet, so we should find it. But for VP, it's already given. It's 0.6. So we write it's equal to 0.6 T. Okay? Now, in order to continue, we should find T. And to calculate the useful power, we should be able to calculate what is the tension in the cable. Who will tell me how we will calculate the tension in the cable? What should we do?
And use the second law of Newton.
Yes, of course. For what we will use the second law of Newton?
We have the acceleration at C.
Very good. So we will take C now. We'll take block C. Okay. For block C, we have the weight. Okay. And we have, what is the other force acting on it?
We have two tensions.
We have 2T, okay? Why we have 2T? Because if we take this pulley, so the force up is equal to 2T. So we have 2T here. and we have here W of C. Okay, why we have this? Because we have to see, because if you consider this pulley, which is in general, when I don't mention anything, the pulley is massless. Okay, so you have that at this level, the tension here between this cable here at this level is equal to 2 times the tension in the cable up, because here you are cutting at 2 places. Okay, so the tension here will be equal to 2 times the tension of the cable. Okay, so now if we apply on the box the second law of Newton, we have 2t up and we have the weight down. And please remember that your acceleration AC is expressed in which coordinate system? AC is minus 0.6 in the downward coordinate system. This is why keep doing the second law of Newton in this coordinate, because if you choose the upward coordinate system, you should not forget to put minus MAC. Okay, so to not confuse, take always the same reference. So if SC is downward, write the second law of Newton within the downward frame. So if I write it here, I will take sum of forces on C along the downward direction equals to MAC. Okay, and what do I have? I have, since the positive direction is downward, so I take plus W of C and minus 2T. And since I know the value of MC, so all I have to do now is to calculate T. Okay, you have that the mass is equal to, here when they tell you the 375 Newton crate, this means that they gave you the weight. So to get the mass, you divide by 10. So it's 37.5 times acceleration of C, which was found to be minus 0.6. Minus 0.6. Okay, and now to get T, you replace WC by its value, which is 375, and you get the tension. Okay, and once we get the tension, we can calculate now what P useful. But we didn't finish. Why? Because what they want is not P useful, is the input power. They said determine the power that might be supplied to the motor. So we need to calculate the input power. Okay, but since we have the efficiency, we know that the efficiency by definition is P useful over P input over the power that we input to the motor. Okay, so now since we already calculated P useful, we can say that P input is simply P useful over the efficiency, which is 0.85. Okay.
Doctor,
Yes.
if you wanted to do P useful at C, you would have to do the summation of each force dot vector.
No, look, if you want to use it at C, the tension here at C, what is the force that is delivering, if you want, that is leading to lifting up C? It's 2T. Okay? يعني أنت at C, what is taking C upward? It's the tension, this one, 2T. 2T is
Yes.
driving it upward. So if you want to put the useful power at C, you will say that P useful for C, it is equal to T at C times velocity at C. And the tension at C is 2T. So you get 2T, but the velocity of C is Vp over 2. So Vp over 2. So you go back to the same formula, which is T times Vp. Because here you have double tension, but the velocity is half. Okay?
Okay.
So
Okay.
you will get again equals to TVP, which is the result we used previously. Any other question on this problem?
Yes, doctor.
Yes.
When you wrote the second law of Newton,
Yes.
you took the system, acceleration down,
No,
right?
look, I didn't. No, look. A is algebraic value. It can be positive, it can be negative. This is why when I replaced A by its value, since I did my calculation previously, I replace it by minus 0.6. Okay, so when you choose your coordinate downward, this does not mean that you are saying that your system is accelerating downward. But why I choose it downward? Because when I calculated my acceleration before, I calculated based on this frame. So when I obtain A equal minus 0.6 for C, this is based on S of C downward. So now if you take S of C upward, you should pay attention to not replace AC by minus 0.6, but to replace it by plus 0.6. So to avoid the confusion, since you already worked in the downward coordinate system and you obtained for this system, which is downward, that AC is minus 0.6, then you will work based on this. Okay, so you can continue based on the downward system, and when you replace AC, you put minus 0.6 instead. While if you choose to shift to an upward coordinate system, you should put attention to put minus MAC, and then minus minus will give you plus.
Okay, thank you, doctor.
Okay. Now, for the last part, we have conservative forces and potential energy. So this part, I think you are familiar with it from school. It is a very simple part, okay? And it's a particular case, if you want, of the work and energy. So the work and energy principle will always work in all situations. However, the conservation of mechanical energy will only work if all forces acting on the particle and if all forces doing work will not lead to losses. Okay, what does it mean that I have a conservative force? A conservative force will produce a work, okay, that is independent of the path of motion. This means that, why here I can say that no losses, because whatever is my path, if I go from one point and I reach the same point, the work will be the same. So example, if I move, for example, if I have an object initially at this point and I move it to point 2 here, okay? If I go, instead of going straight from 1 to 2, if I go up, then go down, for the work of the weight, it will not be affected. Why? Because we have demonstrated together that the work of the weight is what? The work of the weight is just minus W delta Y. Okay? So it's only function of delta Y, which is Y2 minus Y1. Initial Y and final Y. So we say, for this case, we say that the work of the weight is independent of the path of motion. And this indicates that we don't have losses, because whatever is the trajectory we take, if we go back to the same point, we have the same work. Who will give me an example of a non-conservative force that will depend on the path of motion? Friction. Okay? Why friction is not conservative? Because more you move, you know that friction will lead to losses, because more you move, it will try to oppose your motion. Friction is always opposing your motion. So if you go up, friction is down, and if you go down, friction is up. So friction will always lead to a negative work. Okay, and higher is the path, the distance moved, higher will be the losses by friction, which is not the case for the weight. Okay, so from here we can say that when we have friction in a problem, we cannot apply conservation of mechanical energy. Okay, since the work of friction will be negative and it will depend on the path of motion. So what we will do here is that when we only have forces that are conservative, we can apply conservation of mechanical energy. And whenever we have a force that is not conservative, we go back to the principle of work and energy, which was developed before. Okay? So the main conservative forces that we will deal with are the weight and the elastic spring. Why also the force of the spring is conservative? Because if you remember, we have developed the work of a spring on a particle. The work of spring on particle was equal to what? Was equal to half K delta L1 square minus half K delta L2 square. So also for the spring, the work only depends on the initial and final state. Okay. So also in this case, I can say that it's a conservative force because the work only depends on state 1 and state 2 and not on the path of motion. Okay. Now, when we have a conservative force, we can define what is called potential energy. So you know that we have the main two types of potential energy we work with is the gravitational potential energy and the elastic potential energy. For the gravitational potential energy, you need to select a reference, a datum line, okay? And the choice of your reference will not affect your result because at the end you care for delta y. So whatever is my reference, delta y is the same, okay? Now, if you choose a reference, once you choose it, when you are above the reference, you have a positive gravitational potential. And when you are below the reference, you have a negative gravitational potential, okay? So Vg is given by Wy. So when y is up, positive, Vg is positive. When y is downward, then when I am below the reference, then I have a negative potential energy. Now, what they are saying here, that if you choose a y-axis that is positive up, if you choose a y-axis positive upward, then the expression of Vg will be plus Wy. Because when y will be positive, it will give me a positive Vg. And when y is negative, it will give me a negative Vg. On the other hand, if you choose your y coordinate downward, then the expression of V will be minus Wy. Because in this case, it will be opposite. So when y is negative, I need to have a positive result. Because when y is negative, then I am above the reference. This is why we put minus. So keep in mind, if you work with y in your problem axis, y-axis upward, you put V gravitational is plus Wy. While if you are working with y downward, then you put the gravitational potential equals to minus Wy. Now, for the elastic potential energy, it is half K S squared, okay? Where S represents the delta, it's delta L, is the stretching or compression of your spring, okay? So please pay attention. Here we put S squared because the unstretched position is at S equals 0. But if in a problem they consider the unstretched position not at S equals 0, you cannot say the elastic is half K S squared. You should say it's half K delta L squared, and is a stretching or compression of the spring. But in particular, when you choose the unstretched position corresponding to S equals 0, then delta L, which is the stretching or the compression, will be equivalent to the coordinate S. And as you can see, the elastic potential is always